This conference will now be recorded.
Thanks very much, Jill, and thank you for the invitation to come and talk to the section today. So what the subject for today is, and this is the talk in two parts, is we're going to talk about basic steel metallurgy and the effect of rail section on stress and rail defect growth. So the first part we're going to look at, right, what's that? Has my slide moved on? Nope.
Just click on the slide, Andy.
Oh, there we go. Yep, that's gone now. This is a bit of a lag, I think. Right. So the part one, we're going to talk about basic steel metallurgy. I should say this talk's really aimed at perhaps track maintenance engineers. It's not intended to be a treatise on the details of steel structure and all the rest of it, but it really is to try and bring home some of the key things that you need to consider when you're actually managing rail. So in this part of the talk, we're going to talk about phases and crystalline structures very briefly, because that's important to understand as part of the concept. We're going to look at the iron-iron carbide equilibrium diagram to see where steels fit in amongst that. We're going to discuss the effect of carbon content on steel properties. And then importantly, what happens to steel when it's heated and why it is important to actually control that. So, as all good railway activities, we'll start with a cup of tea. So let's think about phases and crystalline structures, and it's quite important to understand what phases are. So I was taught this using the cup of tea analogy, which I'll do with you. So in any system of solids and liquids and gases, there are recognizable phases, that is parts of the whole which are separated from each other by definite detectable boundaries. So if we take the example of a cup of tea, so you make a cup of tea, take the tea bag out, and the mug will be filled with a brown liquid in which is dissolved a little of the organic matter from the tea leaves. So assuming that the leaves haven't escaped from the bag, the result is a one-phase system. So it's impossible to detect any boundary between the colourless water and the brown organic matter because the latter is in true solution. Now suppose we add a couple of spoonfuls of sugar to the tea. So this will not immediately dissolve, and the sugar grains will be for a time possess a separate existence within the tea. In other words, we now have a two-phase system until all the sugar is dissolved, when once again we shall have only a clear brown liquid. Now suppose we let the tea cool down, not merely to room temperature, but in a freezer, taking it down below the normal freezing point of water. The small quantity of brown organic matter will not come out of solution when the mass turns solid, but will remain in solid solution with the water and form a brown ice. On the other hand, the sugar will definitely start to crystallize out as the temperature falls. So water and tea in a solid state remain as one phase, but water and sugar revert again to two phases. And this system is analogous to the behavior of carbon and indeed other alloying elements when dissolved in molten metal. So this is the iron carbide, the iron-iron carbide diagram for steel. So over this side, the horizontal axis is the carbon content, yeah, and the vertical axis is temperature. So up the top here, we have liquid iron and carbon, yeah, and it solidifies when it reaches the upper critical limit, and it transforms as we go down. So it changes, the structure changes a lot depending on carbon content. And the fact that it recrystallizes as it cools. And it's important to remember this process is completely reversible. So the steel goes from liquid metal through the various phases into a solid, yeah. But if you heat it up again, you can actually actually reverse the process and go back. And it's also, as we'll see later when we look in a bit more detail, the speed of cooling affects the granular structure. So looking at the diagram as a whole, this is very low carbon content. So we've got the pure ions down here, which is a very soft material. It's very ductile, quite tough. If you go across to the other side of the diagram, over here, we are actually in iron carbides, which are extremely hard and brittle. And in fact, we use them for actually making cutting tools for steel. So we get a huge range of properties from steel. But let's concentrate on the bit we're interested in. So this is the range we're interested in today, the red box on the diagram. Which is the range of the rail steels, and they have a carbon content from around 0.4 to 0.6 for a grade 220 steel. That's the basic, the old normal grade steel, up to the hardest heat-treated steels like grade R400 HT, which have a carbon percentage of 0.9 to 1.05. So it's quite a small area of the iron carbide diagram that we're interested in for steels. So if we zoom in on that, part of the diagram. So what we can see there, so this is just covering the bit that we're interested in, the red box again. So at normal temperatures, these steels have a perlitic structure, hence their name. We talk about perlitic steels for rail, don't we? At 0.83% carbon is the so-called eutectoid steel, and the structure of which is pure perlite. So at lower carbon percentages, that's over this side, the steel will be described as hypo-eutectide and will comprise a mixture of ferrite and perlite. And at higher percentage carbons, that's over the other side of this point over here, we comprise cementite and perlite. So what effect does this actually have on the properties of the steel? This diagram, which is extracted from the PWI's book, gives you a good idea of that. So the diagram shows the effect of carbon content on steel properties and microstructure. And again, the red box is the range of rail steels that we're particularly interested in. So what are the key points? So as the carbon content increases across here, yeah, the tensile strength, which is the black line on the chart, increases, the hardness increases, which is the green line, and the ductility, which is the red line, reduces. So higher carbon steels are harder and more resistant to wear, but this is at the price of a loss of ductility, so they are less tough. And we will look later at how this has an effect on the critical defect size. As seen, the iron carbide diagram, equilibrium diagram, rail steels are largely perlite, with ferrite and perlite below the eutectoid point and cementite and perlite above. And this is the desired structure we wish to attain, both at manufacturing, following any heat treating, but also following any welding or grinding work that we might wish to perform. So, as I noted at the beginning, there is a time element to the transformation of the crystalline structure in the steel. And this is the time temperature transformation, TTT diagram, for a typical 0.5% carbon steel, which has been heated to 825 degrees C for 15 minutes. So we've taken our steel, we've heated it up for at least 15 minutes, okay? The two curved lines represent the start and the end of the transformation, these two curved lines here. So the diagram illustrates in a simple form the effect of temperature and time on the start and the end of transformation process. From an austenite, because austenite is the form steel exists in when it's molten, to other phases. And a carbon steel transforms fairly rapidly, giving a curve of the simple form shown here. So as you can see from the transformation curve here, yeah, if we do a transformation at 450 degrees C, yeah, so if we did that at constant temperature, the actual transformation commences within seconds of starting. This is a log scale at the bottom. And in less than a minute, it'll actually have completed its transformation into ferrite and carbide. Similarly, if we actually did that transformation at a higher temperature, say 680 degrees up here, in this case, if you look at it, the transformation wouldn't start till about 20 seconds, yeah, and it would take about an hour to finish. So this methodology can be used to control processes, and particularly industrial processes where we actually desire to give specific properties to the finished product. So I think it's important to remember that we don't actually practice isothermal cooling on our site, do we? We just let the rails in generally naturally cool, and we need to guard against what will happen. So things like ambient air temperature, the rail temperature, the preheat level in the rail, and that all have an influence on the transformation. So moving on from there, so it's another quite complex looking diagram, but it shows the relationship between the time transition curves and the curves representing continuous cooling. And again, it's for a plain carbon eutectoid steel rather than rail steel, but it does absolutely demonstrate the point I want to make. So as with the TTT curves discussed in the previous diagram, the bold curves represent the beginning right. Does everyone still see the screen okay?
Yes, we can be.
Right. You see it now? Something's happened, upset my...
Yeah, we can see the screen, the relationship between TTT curves and the curve representing continuous cooling.
Right. Well, I can't see my screen now. So something's happened. Another window is on top of your shared application. Oh, sorry about this. Right. Can you still see my screen?
Yeah.
I don't know what's happened here, I'm afraid. Right, okay, we'll carry on. Let's make this a bit bigger. So as I said, the bold lines represent the beginning and the end of the transformation. The fine dots are the isothermal curves, and these are the structures produced isothermally, that is cooling at a constant temperature, yeah? The chain dots represent the constant rate cooling, and we've got 4 shown on here. So curve A represents the cooling of approximately 5 degrees centigrade per second, yeah? And here the transformation begins at X, yeah? It's completed by Y, and the resulting structure will be a fine-grained perlite. And this is the type of crystallized structure we desire in our rails. Curve B represents a very rapid cooling rate, yep, which is this one here, yep, of approximately 400 degrees C per second. And this is typical of the conditions you get during a water quench. The transformation will not begin until about 220 degrees, yeah, when martensite begins to form. And the structure will consist of 90% martensite at 110 degrees, and so will contain a little retained austenite at room temperature. Curve D represents a cooling rate of about 50 degrees per C, yeah, and as you can see, the transformation starts at point P with a further formation of some fine perlite. The transformation is then interrupted in the region of Q, and does not begin again until Martensite formation begins down at point R. Thus, the final structure at room temperature is a mixture of perlite, Martensite, and traces of retained austenite. So what are the key points to note out of that? Well, in order to end up with the crystalline structure that we desire, it is critical to manage the cooling rate, and the formation of Martensite, which is extremely hard but very brittle, is very undesirable and not what we want from our rails. So if we think about it, how do we actually control that on site? So we need to actually control the heat input when we're grinding or welding, and particularly with grinding, by not attempting to remove too much metal in one pass and by not using excessive force on the stone. And the colour of the steel as it cools indicates that the temperature has been treated. So if it's turned to a dark blue colour, it's indicating, that we call bluing, that we've got excessive heat in the surface. This will be quickly chilled by the cold rail underneath, and we end up with martensite in the surface layer, and hence the risk of cracking forming. Okay. I've got some problems here. Excuse me a moment. Right. Okay. Right, I've got my things going again now. Okay. Right, so let's carry on talk about alloy steels now. So in practice, we've been looking at what happens with pure carbon steels at the moment. So we've seen that carbon content of carbon steels, the effects of structure and carbon content, heat and cooling mode. And this is an oversimplification, but illustrates the key points and shows the process. It shows that the processes need careful control, both at the works during manufacture and on site if successful welding and grinding is to be carried out. Inevitably, in the real world, there's a lot more complexity. And if you want to learn more about that, I think the PWI book is a really good place to start. But the effect of other elements added to the steel to form alloys will modify the processes described. For example, moving the transition curves to the right, moving the eutectoid point, increasing the hardness, or making austenitic or bainitic structures stable at room temperature. So common examples of alloys are silicon and manganese, which change the properties of ferrite by going into solid solution and hardening it, whilst nickel both hardens and toughens. All these can assist with steel manufacturing processes and delivering the desired properties in the finished product. So a familiar alloy of steel in the rail industry is Hadfield's or Austenetic manganese steel. And this is used in the past, both for rolled rail and for castings, but it's now only used in cast crossings. In this, 13% manganese is added, and this allows the austenite, which is the normally present in the molten state, to remain stable at room temperature so that it does not transform into ferrite, perlite, or martensite. In fact, the upper critical transformation is depressed to below room temperature. And the result, as we know, is a tough austenite, which during service, when subject to abrasion and wear, has the effect of changing the outside surface to a very hard martensite, which is very wear resistant. It does have its benefits, however. It's hard to drill or machine because of the work hardening ability, and recrystallization will commence at around 260 degrees C, allowing carbon diffusion, and thus great care is needed when carrying out welding of manganese steels. Right, so it's really important when we're actually planning our welding work to identify what steel or steels we are working with, and hence the correct welding techniques and consumables to employ. And this table shows both the EU and UK grade steel grades and how they are marked on the row. And then below the table is an example of R350HT branding in accordance with the EN standard. So DO is Donawitzy, which is the rolling mill in Austria. The manufacturer is Voest-Alpine, and the bars to the right are R350HT, and 21 is the rolling year, and the rail section is 56E1. The key point to note is that to establish the rail parameters as part of the scoping work includes the rail steel, the rail section, the amount of wear, and the proximity of previous welds and joints. And clearly, if you don't establish this at the work scoping stage, you're going to end up with a poor plan. You'll have the wrong consumables on site, potentially, possession overruns, a failed weld. And it's interesting to note that the most common cause of failed thermit welds is we've actually put the weld in the wrong place. It's too close to another weld. So you might have to clamp the weld. It could also result in a broken weld. And in all cases, it's likely to result in abortive work and costs. So let's have a little look at the consequences of not actually controlling the heat when we actually do work. This is a report prepared by British Steel to support an investigation into a broken trimetallic weld that was discovered during basic visual inspection at Letchworth. So let's explore the report and see how we can apply what we've learned so far. So for those of you who are not familiar with tri-metal welds, this is a picture of one. So a tri-metal weld, it's a process invented by Manoir in France and allows a pelletic rail to be welded to a cast Austenetic manganese steel crossing without the inherent metallurgical problems that would be incurred if this was attempted directly. It is carried out by flashbutt welding a short section of stainless steel to the leg end of the crossing. This is then trimmed off, and the pelletic steel leg extension is then flashbutt welded onto the stainless steel, and the resulting stainless steel insert is between 15 and 35 millimeters thick, typically around 20. Its key benefit is it avoids the use of fish-plated joints, and the inherent maintenance issues and risks that they pose. So let's explore the report and see what went wrong. So these are the fracture faces of the broken rail. So view A shows the whole of the fracture face on the AMS side of the brake. View B shows an enlargement of the rail head on the AMS side of the brake. And view C shows an enlargement of the R260 rail face. And it's the R260 rail which has failed. So the crack initiated below a weld repair in the rail head. It is then grown as a fatigue crack, and you could see the beach marks there, until it's reached critical size. Yeah, and that's the critical size. And then the rest of the rail has just failed by brittle fracture under overloading, which is the rough surface we can see elsewhere. So what else can this tell us? So let's look at some more detail in it. So these are some, pardon me. So what was the peak hardness in the heat affected zone? So these are two graphs extracted from the report. The top graph shows the Vickers HV30 hardness across the weld from the cast crossing through the stainless steel insert and into the parent R260 rail. That's the heat affected zone. That's the R260 rail in general. Okay. So the mean hardness of the AMS was 220. yeah, HV, and the mean hardness of the unaffected parent steel was 282 HV30. Okay, so that's without going through the repair. If we now look at the other section, the bottom section shows the micro Vickers hardness through the manual metal arc weld that had been done to try and repair a defect on the top of the tri-metal weld. And this shows a peak hardness of 786 HV as opposed to around 287 in the parent metal. This level of hardness is an indication that the material was untempered martensite at this location. And it is from this martensite, which is very hard and brittle, that a crack formed, which eventually led to the failure of the rail. So what was the likely cause of the martensite formation? Well, a significant portion of the martensite in the manual metal arc repair was of the R260 steel, indicates that the tri-metal zone will have been cold when it was welded. Probably because only the AMS side of the tri-metal zone was targeted for weld repair, and insufficient thought was given to managing the heat in the pelletic rail. And the effect would have been that the cold rail would have very rapidly cooled the weld deposit. And we saw the effect of quenching is basically you don't transform, you just go straight down until you form martensite. And that would have led to the formation of the martensite in the weld. So why is it important when welding tri-metal zones? Why are they so complex? So the restricted zones specified in our welding standard, this is Network Rail's welding standard 0132, are due to the different heating requirements of AMS and R260 respectively. So AMS cannot be heated beyond 260 to 275 degrees C, as we've said, because you get carbon diffusion caused at these elevated temperatures, leading to a breakdown of the steel. So it no longer remains stable austenite. And as a result, we have a restriction of a maximum interpass temperature of 204 degrees on the AMS side. Conversely, R260 steel has a minimum preheat requirement of 343 degrees C, and the aim is to provide a slow enough cooling rate, so you put lots of heat into the rail, to avoid the undesirable microstructural phase transformations if you suddenly chilled the well. So how do we actually control this in practice? Sorry. So in practice, what we do is in our management standard, we actually talk about needing to actually control this. So we don't normally allow head repair welds within 300 millimeters of the stainless steel insert on the pelletic leg end, or within 20 millimeters on the AMS leg end. So, and only under very specific conditions with very careful site supervision do we actually allow repairs on these welds. And as you can see, it is quite difficult. This is a particularly complex situation, but it is very difficult to manage the situation properly. So what are the key points from this part of the talk? So the key points are that steel has a granular structure that is affected by carbon content, temperature, rate of cooling, and alloying elements. The recrystallization process from molten metal to solid state is fully reversible, and care is required with any process that imparts heat to the rail that the desired structure, for example, a fine-grained perlite, will be present at the end of the process and no inadvertent structures are left. So that's the end of part one. So part two, we're now going to go on to have a look at the effect of the shape of rail section on defect growth. And there's a little exercise in here. So if you've got a sheet of A4 paper handy, you can have a go at the exercise. This is really trying to illustrate what's going on. So in this part of the talk, we're going to look at rail sections and their properties, the effect of shape on structural properties, the bending of beams, residual stresses, which are a factor in rolled sections and indeed in the life of the rail. And then we'll have a little look at how that affects defect growth and defect size, critical defect size. So for each rail section, of the modern sections, there's an REPW drawing giving the important dimensions and informations and the section properties. REPW 792 is for SEN 56E1 rail, which is the one I've got shown there. And these are supported by Euro norms standards giving rolling and material quality tolerances. Network Rail's own standard, TRK 061, called Politic Rails, contains the manufacturing requirements, including testing and chemical composition. And together they form the specification for the supply of Politic rail sections. Similar specifications exist for other track components such as cast AMA crossings. Rail, however, is not like a normal structural steel element in a building, for example, which will become part of a structure and will not be exposed to rolling contact or mechanical wear. Thus, for building steels, a low-carbon mild steel can be used that is tough and easy to weld. Rail has to withstand rolling contact to the head, which will also result in wear and can result in rolling contact fatigue. So a rail needs to be wear resistant, be resistant to abrasion, be strong enough to support and guide trains while spanning between the sleepers, be resistant to impact loading, for example, from things like wheel flats and out of round wheels. It must allow the application of fastenings to hold it down, and it must allow jointing by mechanical means and by welding. And this involves a compromise, and we've seen that as carbon content is increased, we get stronger, more wear and crack resistant rail, but at the expense of losing fracture toughness. So let's consider the effects of section on strength. So as a little practice, I'll give you 3 minutes to have a go at this. So your task is to find a way to support your mobile phone, not less than 3 inches above the desk. And once you've made your support, you mustn't touch the phone or the support. And you've got 3 minutes and a single sheet of A4 paper to actually have a go at this. And we'll see how we go. Right, I'll set my timer. Is anyone having a go? So. Yeah. Yeah, some good thoughts coming in there on the Right, okay, so that's not quite 3 minutes, but we'll have a look at what this is. What oh, I'm having interruptions again. Hang on a minute. Right. So this is what I came up with, and I think a lot of you have probably come up with similar things. So I made a couple of solutions. One's a tube, and the other one is a triangular thing. Yeah, you could probably do it just by folding it as well. So, okay. So what does that demonstrate? So what we're looking to demonstrate is that the shape has a huge role on how a structure reacts to loading, and hence the deflection, strain and stress in the material structure. So the exact same piece of paper can be used efficiently by changing its shape from a flat sheet into a tube. And the effective shape is described as the second moment of area or moment of inertia of the cross-section, and is expressed as IXX or IYY. So if we think about some other examples of that, so this is the standard formula for a rectangular section. So if you think about it, if I've got a scale rule, and I've got one in my hand, but you can't see me, it's 40 millimeters wide and 3 millimeters thick. So if you actually substitute the numbers into that, in the IXX direction, so bending it on edge, it has a IXX of about 16,000. In the YY direction, so that's bending it in the flat direction, it has about IXX of about 90. So it's about 170% more effective at resisting bending if you bend it in the flat direction, sorry, in the on edge direction than the flat direction. So that's really important. So again, this is about, without changing the shape of the piece of material, it's just how we load it, and it's the orientation of load. So how we arrange the material in a beam is important to the loading, allows the material to distribute in a way that gives the most efficient shape to resist bending, and can be used to get the greatest benefit from the least amount of material used. And by way of another example, just again, I'm just going to talk through this, but that's the standard equation for a tube. So, and obviously if it was a solid bar, then DI would be 0. So if you had a bar 100 millimeters diameter and you rolled it out into a plate 10 millimeter thick, it would be about 785 millimeters wide. And if you then rolled that into a tube, you'd end up with a tube 250 millimeters diameter. And if you work out what the resisting strains on that are, you can actually work out that the actual, for a tube, so we've used no more material, we've just turned it into a tube, so it's no heavier. It would actually be 11 times the resistance of the same material used as a solid bar. So it is really important in terms of making efficient use of material is how that's done. But we're going to really go on to look at how that affects its propensity to damage and cracking. So what happens when you bend a beam? So in the top left of the diagram, we can see what happens. So if you bend it in the vertical direction, it will deflect into a curve. And as the beam deflects, the top surface becomes shorter due to compression, and the bottom surface is elongated due to tension. And through the beam, there will be a plane where there is no change in length, and hence no strain or no stress. And this is the neutral axis. And for a symmetrical section, it will be halfway down. If you plot the change in stress across the section, which is the bottom left diagram, yeah, it will be seen that the maximum stresses are in the extreme fibers furthest from the neutral axis. And that's really important when we consider the stress in a rail section. So this is the general equation for bending. So the stress equals the moment of the neutral axis, the perpendicular distance, y, between the neutral axis and where you're actually considering the loading, and the second moment of area of the section. So for a given value of bending moment, m, it can be seen that the bending stress increases with increasing y. That is, the bending stress is highest at the extreme fibres, furthest perpendicularly away from the neutral axis. And the larger value of IXX, which is the shape that is more effective at resisting bending, reduces the overall stress. So let's think about our rail again now. So what can we see about our rail? Well, first of all, it's asymmetrical in the vertical direction in bending because the head and the foot are different shapes to perform different functions. And as we've said, the head is to have a good rail wheel interface, and the foot is about supporting the rail, spreading the load into the sleeper, and allowing the fastenings to be applied. In the YY direction, it's symmetrical because we want it to be that way. We don't want it to be more difficult to bend in one direction than the other. And if you see in the red box in the chart, the IXX is much greater than the IYY dimensions, And this is because we want the rail to resist bending in the vertical direction from train loading, but we want the rail to bend easily and smoothly into a large radius curve to follow the railway alignment, as I said, I've highlighted in the red box there. So in the vertical direction, the most highly stressed places are those furthest from the neutral axis. Thus, the crown of the rail is subject to the highest compressive stress in bending, and the rail foot is the most highly stressed in tension, which is more likely to cause cracks to grow. In the horizontal direction, the most highly stressed places are those furthest from the neutral axis, and thus the edges of the rail foot are the most highly stressed. In reality, the loading and hence the stress distribution is complex, as the rail is loaded both vertically and laterally, which leads to torsion in the section of the rail as well. And it will be subject to residual stresses, typically from roller straightening of the finished rail, and these will have an impact on the fatigue and fracture toughness. And remember that thermal forces are distributed uniformly across the cross-section, and for most of the year, rails are in tension, as the rail temperature will be below the stress-free temperature. And again, this will cause crack to grow, but is obviously the key to resisting track buckling. So this rather colourful diagram, it shows the stress distribution in new and worn rails. So, and this is a result of the way the rail is rolled, the way the rail is cooled, the way the rail is then straightened after the process. So the tensile stresses are the ones tending to red, and the compressive stresses are those negative are tending to blue. And the more intense the colour, the larger the stresses. So tensile stresses encourage crack growth, whilst compressive stress tends to inhibit crack growth. With new rail, note the concentration of tensile stress in the foot, but the tendency to compressive stress in the edges of the foot. This comes from the cooling of the rail after rolling and subsequent roller straightening of the finished rail. With wear and metal flow over time, the stress becomes redistributed through the section. There is a build-up of tensile stresses in the head from plastic flow and a concentration of compressive stresses close to the crown of the rail due to wear. In the foot, the tensile stresses remain, but note the build-up of compressive stresses at the edge of the foot. So let's think about two defects in a piece of rail. So let's choose a piece of 1969 113A flat bottom rail, and it's got two defects in it. So we've got a small inclusion from the steel making process in the center of the rail head. And we've got corrosion of the underside of the foot of the rail caused by poor pad conditions. So let's have a think about which is likely to grow and what are the factors affecting it. So let's think about the inclusion in the rail head. So it's in the center of the head, so it's readily detectable and can be monitored for growth. And it leads to things like the Tascheval type defects shown on the right-hand side of the screen. It is closer to the neutral axis, so the stress levels are slightly lower. Over time, it may initiate a Tascheval defect, that will grow slowly by fatigue under bending and thermal loading. And the critical size of a Tascheval is quite large before the rail will fail by brittle fracture. And it's likely, very likely, that the defect will be detected before this reach. So on the right are two pictures of the fracture faces of broken rails that have a Tascheval defect. Whilst one has failed at quite a small size, the other has grown to fill most of the railhead before fracture occurred. And this variance could be due to an unexpected impact load or due to high tensile rail stresses in the rail when the weather is cold, because the rail temperature is below the stress-free temperature. The corroded rail will develop slowly over time, but as the rail is already old, corrosion pitting on the underside of the rail foot is likely to have developed, and poor pad condition will exacerbate this. So corrosion pits on the underside of the rail are not ultrasonically testable unless they lie underneath the web, because remember, we look down through the rail head when we're testing things. So corrosion pits that are well out from the rail head are very difficult to find. Over time, the surface corrosion may initiate a fatigue crack in the foot of the rail, and this will grow under the effects of bending, particularly where track conditions, support conditions are poor. And it is further from the neutral axis, so the stress levels are higher. And what you will notice is the critical size of a corrosion pit crack is small before the rail will fail by brittle fracture, and it is likely that the effect will not be detected before this is reached. And things like these are actually dominating rail failures now. So on the left-hand side picture are the views of the rail that has failed from a fatigue crack from a corrosion pit in the foot. So note how small the crack is. This type of failure is often driven by poor track geometry associated with poor support, and often occurs at locations like the run-on or run-off of direct fastening bridges, or where poor support conditions pertain for an extended period of time. So what's that telling us? Well, what we can see is some defects, and this is some examples, thanks to Brian Whitney. So if we got things like Tascheval type defects, so this is a plot of defect size against time. With the slower growing defects like Taschevals and things like that, not only are they more readily detectable, but you have much longer, it grows more slowly, and the critical defect size is much larger, so you've got a much better chance of finding it before you fail. The problem with the other type of defects, things like the corrosion pit defect, is they grow quickly. So as you can see, the P to F interval shown on the chart is much shorter, and also the critical defect size is much smaller. So that's one of the reasons why these defects are more likely to run to failure before we actually detect them. So what are the key points then? So just to really wind up this part of the talk. So the cross-sectional shape of a rail section has an effect on the stress distribution. The stress under load is largest in the extreme fibres further from the neutral axis, and rails are subject to stress caused by residual stresses from the manufacturing process and from wear and metal flow. They're just subject to bending and impact load from traffic, and they're subject to thermal forces dependent on the stress-free temperature. And it's important to remember that tensile stress drives fatigue and crack growth in rail. And that's the end of the presentation. So I'm more than happy to take some questions.
Well, thank you very much, Andy. So if you've got any questions, please put them in the chat.
Yeah. So I'll stop sharing for a minute and then I can go back into it if we need to. Right.
So a question from me, Andy, waiting for others to chip in.
Yeah.
What type of defect do we normally see through manufacturing process rather than defect developing then under utilization and load?
These days with rail post 78, so rail that made concast, we get actually very few inherent defects if in the rail at all. So the manufacturing defects you tend to see are usually things like surface damage and things like that, which are weeded out before they get into track. With the rails manufactured prior to 1978, and particularly prior to 76, which were made by the concast, the ingot process, then there is a risk of inclusions within the rail section, which are actually formed in the ingot. When that's rolled out to the rail, into a rail, that's what causes things like longitudinal vertical splits and small inclusions in the head, which can, over time, under fatigue, grow to okay. Yeah, it's all right. Will grow over time to. You still there?
Yeah, still here, Andy.
Okay, right.
Okay, Phil, you've got a question.
Yeah, thanks, Andy. Very, very interesting, and good to brush up on my bending stresses and things. I haven't looked at those kind of formula for a while, but I'm very interested, of course, making the point about the criticality of rail foot corrosion, and how quickly a small defect can grow to failure. So I'm just intrigued or curious to see if there's any developments in non-destructive inspection, testing of rails that are kind of addressing that or starting to manage that risk.
Right. Yeah, that's a really good question. I mean, at the moment, ultrasonically, we can't test them because you can't rely on them being in places where you can actually see them. And also the problem is because of the surface roughness, it is quite difficult to pick them out when they're small enough to do something about. So the focus has really shifted, and Brian Whitney's done a load of work on this, looking to sort of combine. It's about combining data, isn't it? It's about combining track geometry data with rail defect information, rail depth information, corrosion information, and actually focusing on that. But there's definitely a strong correlation between places where we've got poor support conditions, like on and off of long timber bridges, on and off of direct fastening bridges, or places where we've got poor formation. So we've got wet beds and the track's voiding quite badly and things like that. Because it is the stressing of the rail, yeah, that actually causes these things to grow. So I think that the current feeling is probably we need to focus more on a combination of looking. So where we've got corrosion forming on older rail, we need to be more vigilant for longer term things like dip angles and things like that.
Okay, thank you very much.
Okay, no problem. Right.
Are there any other questions? Yeah. No, there's none in the chat at the moment, Andy.
Okay.
So what I suggest, Andy, and that's another question coming very quickly, is just to thank you on behalf of everybody for a very interesting talk. Same as Phil, it's very interesting to go back to well, what I've probably last looked at university about bending moments and the behavior of material. But it's for me, it's critical as engineer that we go back to first principles, but for understanding actually what is happening on the railway and helping the decision we made. So I think today you certainly make a case, for thinking back to these first principles. A very interesting presentation, and I've learned a lot about the phases of metal, the importance of temperature and cooling time. And some real, real life example that really illustrated, your talk in the railway. Plus a very interesting practical exercise as well. I think people have engaged with that. Certainly Frankie and Rich in the chat, seem to have a bit of fun with it. So again, on behalf of everybody, thank you very much. And goodbye to all the attendees.
Okay, thank you very much, everyone, and I shall see you all again soon. Okay.